have Vikesh Siddhu from, actually, I'm not entirely sure. He'll tell us. No, wait, number 4 is Jilla. And I assume Platypus has something to do with Graeme and or John Smolin. Yes, check. Okay, we're ready to go.
All right. Hi, everyone. I'm Vikesh. I'll be talking to you about Platypus of the quantum channel zoo. The sort of key motivation or the place where this story kind of begins is to ask how much information can a quantum channel send? Now, in order to answer this question, one way to go about it is to think about the quantum analog of Shannon's theory and try to define the capacity of a channel for sending information. And so one can carry out this procedure and define a channel's capacity. And once this capacity is defined, unfortunately, as we saw from the last talk, these capacities are usually hard to compute. And so that's a problem. But suppose you can compute it, then another problem is, well, how do you achieve the capacity? What, can you write down a good error correcting code that will sort of give you the capacity of the channel? Turns out that's also not entirely trivial, and it's a difficult problem to solve. But suppose you can actually solve that and achieve the capacity. So now you're in really, like you've kind of got very far with this program. But it turns out that doesn't mean that you understand how much information the channel can carry. Because it's possible for a channel to sort of assist other channels in sending information, even if it can't itself send any information. And so why is it that we don't really have a simple answer to this straightforward question? Well, maybe the question isn't meaningful as it should be, or as meaningful as it should be. And that is at least our current understanding, that actually the question is not as meaningful as it should be. For instance, I can take 2 channels for each of which I know the capacity. I can hook them up together and have a new channel. I know its capacity, and I ask you, how much of the information carried by the joint channel is being carried by the individual ones inside it? How many of you want to answer that question? It's not a good idea to try and answer that question. The reason is it's possible that 2 channels that can't send information themselves can be joined in this way such that the bigger channel is sending information. So asking how much is coming from the individual ones is not going to make much sense. And so it's kind of a weird deal to think about these concepts. And, but we're going to do it anyway. And here's how we're going to do it. First, I'm going to define this capacity in some operational way. In the previous talk, I got a lot of help, so I'm going to try and move fast in this one. The idea is that you have one person trying to communicate some information to another. And suppose you take T joint users of a channel N and are able to send T times R units of information in such a way that as the limit of T tending to infinity, the error in which amount of information you send tends to 0. And R is here said to be an achievable rate. The maximum such achievable rate defines the capacity of this channel. And then depending on what type of information you're sending, classical, private, or quantum, you get different capacities. And I will focus a little more on the quantum capacity, but there will be statements about other capacities as well. Then, of course, I have defined it operationally. You want like a sort of tool to calculate these things. And before I get there, I'll review some material from the previous talk. The way to think about a channel is that it sort of has an input system. There's an isometry that couples the output and the environment. You don't have access to the environment, so you trace it out. So you get a channel from the input to the output. That's the orange line N. But you could have traced out the output. You'll get the complementary channel. And now you can, the second ingredient here is the von Neumann entropy. It's just for a density operator rho, negative trace of rho log rho. And the first quantity I want to talk about is an achievable rate for sending quantum information. It's the channel current information. And it's obtained by subtracting from the output entropy, the entropy of the environment channel, and maximizing the quantity over all possible input density operators. It bounds the channel's quantum capacity from below. But capacity can be written, as we saw in the previous talk, as a regularization of this type. This is very hard to compute. And similar statements can be made about private and classical capacities. Next, of course, there are some problems with what I just said. In the computation part, for instance, the quantities I defined can be super-additive. Essentially, that means that channels used together can send more information than used separately. And this comes up mathematically, say, in one way. So channel coherent information is one way of achieving some amount of quantum information you want to send. Two channels used together can send strictly more, can have strictly larger coherent information than the sum of each. One can define cases where this doesn't quite happen in the following sense. So you can have a channel that's weakly additive in such a way that if you use it with itself several times, the coherent information is additive. Or you can have some strong additivity for a channel, and if you use it with any other channel, its coherent information of the joint channel remains additive. Then beyond the non-additivity or super-additivity in the coherent information, you can have similar things in the capacity. The capacity of two channels used together can be greater than the sum of the individual capacities. Turns out if one of the channels is actually strongly additive, then that inequality turns it to an equality, which is somewhat interesting that if you have strong additivity, somehow you understand the ability of the channel to send information in settings where it's used with another channel this way. So what's the big deal with super-additivity? Well, kind of it makes it hard to translate classical ideas to the quantum world. That's sort of the message. For instance, it'll make it hard for you to compute this limit. So what do you do? Well, you try to find examples where you have strong or weak additivity and get a handle on those examples, and that will kind of help you understand what's going on as far as transmission of information is concerned. The second is, of course, when you're trying to get this handle, you want to actually quantify how useful a channel is for sending information. So that becomes a little tricky because our original idea of doing the capacity business by itself didn't lead to as full an understanding as it does in the case of classical channels that are point-to-point. Well, with this challenge, I guess the opportunity is to, well, solve those, but also there's to obtain a sort of rich understanding of quantum information, to sort of find sort of error correcting codes that achieve sort of these rates better than the channel's current information. And then maybe there is some way to quantify a channel's resourcefulness that differs from the Shannon idea that I started out with. On the way, we want to start with something simple. And we want to start with where some things are additive. So we start with what is called a degradable channel. Essentially, we can complete this loop from the input to the output and the environment of the channel by taking a channel at the output and applying it so that you get the environment channel. When this happens, there is certain simplicity. The environment channel in this case is called the anti-degradable channel. The simplicity is if you have any two such channels, jointly you use them, the current information is additive. So that's good. And the other simplicity is that the private capacity of any such channel equals its quantum capacity, and that equals its current information. And so you kind of get something in the bonus here. So it's kind of nice if you have this structure. So let me start with the channel with that structure. Let me start with a simple channel, which is degradable. It's a qubit input, qubit output, qubit environment channel. It's degradable, believe me. It's current information and its private capacity and quantum capacity can be computed. But it has such a simple structure that its classical capacity can also be computed. It's just one bit. It has a two-dimensional input. It can't send more than one bit. If you use 0 and 1, they will land orthogonal at the output, so you can send one bit. And so this is simple. Second one is even simpler and more stupid in the sense that it has a one-dimensional output. It can't send any information, classical, quantum, or private. And now I hybridize these isometries that define the channels. So the hybridization functions as follows. It constructs a new isometry that acts on the 0 and 1 states as if it's the first isometry, and acts on the 2 state as if it's the second isometry. So that's a totally reasonable way of thinking about it. And this hybridization gives something unique. But before I get there, I want to take a parallel with the platypus. So when the platypus was discovered down under and reported back in Britain, those viewing the reporting in Britain thought it to be a hoax obtained by sort of stitching two different animals together. And so in this case, a duck's beak on a beaver. But the animal actually is quite unique. And just like this channel, this is something quite unique. What we have for this channel is a variety of additivity of these following types. We believe the channel's current information is additive and equals its quantum capacity. And this statement can be proven up to what we call the spin alignment conjecture. Then we can prove that the channel's private and Holivo private capacity or private information, which is the analog of the current information for private transmission of private information, is additive. And similarly, the channel's Holivo information, again, the analog for sending classical information, is also additive. And so that's interesting. Then we also have more. We have the separation between various capacities of the channel. So we can say exactly what's the channel's classical capacity and private capacity. It's exactly 1 bit. And they're both equal. And we can separate this capacity from the channel's quantum capacity. And the separation is quite large. On the x-axis, I plot in the plot on the right, I give you this separation. And to prove the separation, you can either use the spin alignment conjecture, but you don't have to. You can essentially produce an upper bound of the channel's quantum capacity, which will separate it from the channel's private and classical capacities. So cool. I gave you 2 channels that were simple. I did something to them, hybridizing. I produced a new channel. It's additive like the previous ones I started out with. But kind of the additivity in the things I started out with was pretty clear. Here it isn't. In the sense that you can't prove the additivity in this case of thinking that the channel is degradable or anti-degradable. It is not. And then maybe you think that the additivity is coming from the fact that this belongs to some well-known class of channels for which the channel's Holivo information is known to be additive. It does not belong to such a class. Then you can ask, well, okay, you have separation between capacities. This is known. Maybe this channel belongs to a class for which such separation was previously known. This doesn't belong to any such class for which such separations were previously known. And finally, we have equality between the channel's private and classical capacities. And maybe this belongs to some class of channels for which this was known. To the best of our understanding, there is no such non-trivial class for which these 2 are equal. So, well, how do we prove anything? Well, here's how we do it. For the channel's additivity in the channel's current information, we rely upon our conjecture, which I will state later. For the channel's additivity of the private and Holivo informations, we have a sort of different, we kind of do this straight attack. We first produce a sort of lower bound, or well, let's produce an upper bound. And this comes from the work of Wang, Shi, and Duan from 2017. We produce an upper bound in the channel's classical capacity, and that's 1 bit. Turns out this upper bound is strong converse, which essentially means that if you try to code above the rate at which the capacity is, the error in your coding must go to 1. The capacity itself says that if you code below the capacity, then the error can be driven to 0. And so you get this kind of interesting understanding of when you can send information and what the errors will be like. Then we have this a code, sort of a code for sending private information, which sends 1 bit. And this code is kind of one shot. I produce here 2 states that will land distinguishable at the output, but exactly the same at the environment. So we kind of finish the proof that way. Then to bound the channel's capacity from above to prove the separation, we can use a variety of bounds. They have the strong converse property. And so these include, say, work from Wang, Fang, Duan, also the Werner-Holivo bound, also transposition bound. We can use that. What I've written on the left are these transposition bounds. And I can kind of do tighter numerics than the bound that I've written here. That was what was in the previous slide. Cool. Now we have all these additivities, and that's great. But now I'm going to switch gears and talk about super-additivity. What happens is if we find out that if we use this channel that I defined previously with a variety of other channels, we find that the joint channel's current information is super-additive. And so we tried, say, the 50-50 erasure channel, and the amount of super-additivity I've mentioned on the left. The x-axis is the parameter S, y-axis is the amount of super-additivity. The erasure channel super-additivity is in the magenta line. Then we've checked with depolarizing, found similar results as super-additivity. It's plotted on the left. Then we tried with qubit poly channels. It kind of worked, and then it worked with the qubit amplitude damping channel, and that 50-50 amplitude damping channel case is on the plot. Then we tried randomly generated qubit channels. It still works. So for these reasons, we believe that super-additivity is quite generic in the second channel in this case. And then despite the fact that you have these different channels and you have to obtain super-additivity in each, we find that the strategy in each case is the single strategy that just works for all these channels. And for convenience, I've written down that strategy, which means a density operator over the joint input for which the entropy, for which the current information is going to exceed the sum of the individual channels. And finally, up to the spin alignment conjecture, in cases where the capacity of the other channel is known, we prove we can get super-additivity of quantum capacity in this case. But we kind of don't need the spin alignment conjecture for super-additivity of these types of channels. There's a high dimensional analog of this Platypus channel for which we can prove unconditionally super-additivity of quantum capacity when used with an erasure channel, E lambda of input dimension D. And this super-additivity has the following features. First, it's possible to have something like this. So the capacity, MD channel, which is the generalization itself, has capacity. And then you use it with an erasure channel which doesn't have capacity, but that channel amplifies the capacity which previously existed in MD. And then you can also have situations where we both had capacity, and then you use it together, they amplify each other's, which we call super amplification. And so this can happen too. And then finally, these channels don't need to be the amount of noise in these channels doesn't need to be very high. The capacity is not quite small or something. For instance, at D equal to 5, this MD channel has 20% the capacity of an identity channel of the same input dimension. So it's not a channel which is very noisy in that sense. But of course, as you pump up the dimension, the capacity goes down, and we have an upper bound on the channel's quantum capacity, which I've written down here. And here I plot on the right-hand side a plot between where we find super-additivity of quantum capacity. This comes as, so on the x-axis, it's the dimension of the D parameter in the MD channel, or the input dimension of the erasure channel, or on the y-axis, it's the erasure probability. Between the green and the magenta lines that are dotted, we find unconditional super-additivity. If you believe our spin alignment conjecture, then the region over which we find super-additivity extends further between the solid lines. And now I want to take a second to tell you about the spin alignment conjecture, which essentially is a statement about when is the entropy minimum if the density operator over which you're computing the entropy has some fixed form. The form is the following. It's an arbitrary but fixed convex combination of states that are partitioned into two. One partition is variable, the other partition a product state over states that are diagonal in the 0-1 computational basis. N equal to 1, which means you think of one spin, you could prove this conjecture pretty easily. The conjecture is that all the other spins that were variable are exactly the same. They are the one state, and that's the largest eigenvalue. They are a projector onto the largest eigenvalue of Q. We can solve it for n equal to 1. We can solve it for n equal to 2. And when the parameter S here is a half, for other cases, we can do numerics as much as our laptops permit. And so finally, I want to conclude that this channel is like interesting and weird, like a platypus, which as an animal is an egg-laying venomous mammal with a beak, which is sort of odd. It has features from a variety of other animals from different species, but it is not an animal in any of those other species. And then we finally have a non-trivial family of channels whose capacities can be computed. And we believe that the high dimensional and higher parameter sort of variants of this capacity of this channel, which are defined in the papers, are also worth studying. And we do some kind of studies about those things as well. And finally, kind of the take-home message also is that the super-additivity is usually we find it here to be much more prevalent than previously thought. And finally, please solve the spin alignment conjecture. And here is a picture of the platypus.
All right. So thanks a lot. If there's questions, please come up to the microphone. We have time for a few.
Hey. Is there a natural physical process from which you'd expect the platypus channel to emerge?
That is a good question. we don't know yet, but it's worth looking into. It's because it's a three-dimensional system.
It's pretty simple.
There has to be some kind of decay process that I would imagine works, but it's worth looking into and clarifying that here's how it happens. Thanks.
We have time for one more question.
Small question. Do we know that there's distinction between weak typicality, weak additivity, yeah, weak additivity and strong additivity? Because for the whole information, we know that they are equivalent, right? So in the quantum case?
Yeah, in the quantum case, you can have weak additivity but violate strong additivity, which is what we have in, say, the erasure channel will do that.
Which?
The erasure channel.
Ah, the erasure channel.
Will do that. The Platypus channel, we think, does that too. Yeah.
Okay, thanks a lot again, Vikesh. Okay, we're setting up our next talk.